All right, hello everyone, and welcome to today's lecture. This is the seventh lecture in the series, and today I'll be talking about torque and angular momentum. All right, so first, let's have some introduction. So before we talk about angular momentum and torque, we have to first talk about rotation. So rotational motion is similar to translational motion, but instead of changing your position coordinate, you're changing an angular coordinate. So in translational motion, you might have like go from point A to point B. This is a distance of X. In rotational motion, like instead of moving, you will like rotate. So this would be, say, a rotation of 90 degrees. And, or this would be pi over 2 radians. So how many radians that you moved, this is your angular distance. So we can also define an angular velocity, which is the rate of change of your angular distance, and an angular acceleration, which is the rate of change of your angular velocity. And this is just similar to normal velocity and normal acceleration. It's just for angles instead of position. And the symbols we commonly use for these are omega for angular velocity and alpha is for angular acceleration. All right, so we had some equations of motion for translational motion. And if you remember them, they are these equations right here. And so since the velocity and the acceleration were similarly defined, v equals dx dt and a equals dv dt. If you look at these two equations, they're basically the same as these two equations. So if we go through the exact same steps, you'll get these two equations, which are basically the same, but you can use them for constant angular acceleration instead of the previous, these two were for constant translational acceleration. All right. Now let's try an example. So I will, as usual, I will start my poll. Oh no. Um, Hold on. Yeah, so I'll give you a few minutes to work on this and shoot. Oops. I will try to fix this. All right, we're back. So I'll give you a few minutes to work on this question and feel free to ask any questions or send me your answers. Okay, so it's been about 3 minutes, so let's start talking about this. First, end the poll and share the results. So, okay, so some people chose A and B, and more people chose C and D. Interesting. So I think the correct answer here should be D. Or let's take a look. So first of all, let's look at what's going on. So we have a computer disk, which is spinning, and I'm assuming it will accelerate at a constant acceleration alpha 1 until it gets up to speed. And after that, I guess it will just continue spinning at a constant angular velocity of omega. And then after that, after it's done spinning, it will slow down at angular acceleration alpha 2. And this makes the angular velocity go from omega to 0. So what do we know? Well, we know that as it's accelerating, it will spin up to speed in 10 rotations. And when it's decelerating, it will spin down to a stop in 50 rotations. Okay, that's very cool. So let's look closer at this problem now. So how will we solve this problem? Well, we can use our kinematic formulas. And before I mentioned that we can use the same equations, theta equals 1/2 alpha t squared plus omega t, and omega is omega 0 plus alpha t.
JD.
And we have like the same equations as in the translational case. Like this one corresponds to delta x is half a t squared plus vt. And this one corresponds to delta v is just at, right? But turns out we can actually use the other kinematic equations that we derived from these two. So like, what's one? V squared, V final squared equals V initial squared plus 2a times delta x. We derive this from these two, right? So if we follow the same steps, we can get the same equations. Omega final squared equals omega initial squared plus 2 alpha times theta. And in general, if you have a kinematic equation that works with x and v and t and a and stuff like that, you can probably just replace x with theta, replace v with omega, and replace a with alpha, and you'll get the corresponding equation in rotational motion. All right, so back to the question. I think this equation will be the most useful here because we know what omega final is, we know what omega initial is, and we know what theta is. And if we go back to the problem's just asking us what is the ratio alpha 1 over alpha 2. So we want to find the alphas, and we can do that because alpha is the only unknown in this equation. All right, so let's write down this equation. So first of all, for the accelerating phase, what do we get? So omega final here is just omega. And omega initial is 0. And it has angular acceleration alpha 1. And it goes through 10 rotations, which is 20 pi. All right. So we get that alpha 1 is omega squared over 40 pi. Very nice. Now, what about alpha 2? Well, if we write down the equation, but now we're decelerating, well, its final omega is 0. Its initial omega is just omega. And then it's accelerating at minus alpha 2 and 50 rotations, so 100 pi. All right. And then we get that alpha 2 is equal to omega squared over 100 pi. So now we have the information we need to solve the problem. We get that alpha 1 over alpha 2, omega squared over 40 pi, and omega squared over 100 pi. Sorry, 200 here. And we get that the answer is 5. All right, cool. Any questions, or I will just move on? Okay, then. So let's talk a bit about, what's this, rotational motion to translational motion. So if a rigid object rotates an angle theta, a point r away from it will translate r theta. This is like, I guess, how circles work. So what this means is basically just an object that moves this way. If this is r and this is theta, then this distance will be r theta. And notice that theta here has to be in radians. Otherwise, this won't work. So always use radians. And so basically, if we write a distance s as r theta, we can get that v equals r omega and a is r alpha. So I guess if we have something moving in a circle, we can write v equals r omega, because if this angle is changing at a rate omega, then this distance will also be changing at a rate r omega. So this will be its velocity. And similarly for acceleration. All right. Now let's talk about uniform circular motion. So this is a special case of circular motion, I guess. It's just an object moving in a circle with a constant speed. It's just moving around and around like that. However, its velocity is actually changing here, because if we look right here, its velocity points that way, but a little while later it points that way. And since its direction continually changes, which is, I'm sorry, Do you have a question?
What?
I guess not.
I'm
Let's
totally mad because
let's continue.
I don't know. Focus on what?
Um, I'm sorry, I couldn't really hear you clearly. Do you have a question? Okay, never mind. Let's continue. So yeah, the direction of the velocity is changing, even though the magnitude is not. And so this means that we have to have an acceleration. Well, what is this acceleration? Well, all we have to do to find it is, say, express its position as a function of theta, and theta is a function of time, so we'll get its position as a function of time. So say this is like our theta, then its x position here is our cosine theta, and its y position here are sine theta. So now we'll get its y velocity by differentiating. And notice that theta is a function of time here. So we also have to use the chain rule to add a term d theta dt. And similarly, we'll get our y velocity and x velocity listed here. So like we said before, okay, so this is negative r sine theta times omega, and this is our cosine theta times omega. So then what is this velocity? Well, if you draw it out, all it's doing is it's tangent to the circle as we expected, and its magnitude is the square root of negative r sine theta omega squared plus r cosine theta omega squared. And this is just our omega, like we expected. Okay, now we have its velocity, and we can just differentiate again to get its acceleration. So those were our formulas for the velocity. Now if we differentiate again, we will get these formulas for acceleration. So this is our cosine theta omega squared, and this is negative r sine theta omega squared. All right, what does this mean? Well, if we draw in our acceleration here, we'll find that it's in this direction, and its magnitude is the square root negative r cosine theta omega squared plus negative r sine theta omega squared, and this is r omega squared. So what this tells us is that if an object's moving in a circle with radius r and angular velocity omega, then it has to be accelerating radially inwards, with the magnitude of the acceleration being r omega squared. All right, and this is very important. This is called the centripetal acceleration. And as I mentioned earlier, it's always towards the center of the circle. So any object that is traveling in uniform circular motion must have this acceleration pointed towards the center of the circle. And we can write it as a equals r omega squared, or if we substitute in omega here equals v over r, we'll get that a is also v squared over r. All right. Now let's do an example. So I will also give you a few more minutes and feel free to ask questions or send me your results. Okay, It's been like 4 minutes, so let's talk about this question. So one person chose B, a lot of people chose E, and also one person chose F. And just a quick contest tip, you should never choose F because it's basically never the answer. So yeah, in this case, F was not the answer was E. So it's good that a lot of people chose that. So let's talk about this question. So we have a car here, and it's attached by a stake in the ground. So it's forced to move in a circular path. And the radius of this path is 3 meters. So it's moving in a circle. And initially, its angular velocity is 1 radian per second. And it has an angular acceleration alpha of 4 radians per second squared. All right. And the question says the string will break if the centripetal acceleration, A, it becomes too high, and specifically A greater than 243 meters per second squared. All right. So how do we solve this question? Well, it's actually pretty simple. So if we go back to our formula for centripetal acceleration, the acceleration is r omega squared, right? So the key is to realize here, well, when will the string break? Well, the string will break when omega reaches square root a over r. And when will omega reach this point? Well, we have the kinematic equation omega is omega 0 plus alpha t. So our t will be omega minus omega 0 over alpha. Or we can substitute in this. And so now if we go back to our problem, let's do this. So now if we go back to our problem, we know what A is, we know what R is, we know what omega 0 is, and we know what alpha is. So now we can just plug all of these in, and this will give a time of 2 seconds. All right, cool. You have questions or no? All right. So let's move on. Oop. And now we can talk about torque. So what is torque? Well, let's think about balancing objects here for a second. The idea behind torque is if you have two forces that act at uneven distances on a rigid body like this, well, what will happen if the beam rotates a small angle theta? Well, what would happen is that this end of the beam moves the distance of, say in my example, it was 1 meters and 2 meters. So this end of the beam would move 1 theta, but this end of the beam will move 2 theta. All right. But what does this mean? Well, in my example, we also had a force of 2 newtons here and 1 newton here. Well, this force does 2 newtons times 1 meter times theta, or 2 joules times theta amount of work. And this force also does, well, it does 1 newton times 2 meters times theta, also 2 joules times theta amount of work. Okay, so we see that these two forces, although they're different in magnitude, because of how far away they act from the pivot, they will do the same work while our object rotates an angle of theta. So this motivates our idea of torque, which is basically if we multiply our force by the radius at which it's acting, we get, well, we'll get how much work per angle it does. And this is sort of like a rotational analog of force. So if we want to use energy to motivate this, well, we had a translational force is dE dx, or if we don't want to use calculus, just E over x. Well, we see now that x is r theta, right? So this is E over r theta. So if we simplify this, F times R is E over theta. So what we call this now is a torque, tau. And tau is the symbol normally used for torque. Tau is E over theta. So these two equations are translational and rotational analogs of one another. So we can think of torque as really just a rotational force. And if we want to define torque more generally, what we get is it's actually the cross product of our radius and the force. So if we have a pivot here, and we have a radius r, and then we have a force that's not entirely perpendicular. Well, the torque will be F times r times sine theta. We can think of this as the either theta being sine theta being the component of the force that's in the right direction to apply torque, or we can also think of r sine theta as the lever arm. So how much leverage we're actually getting from our radius. But anyways, yes, torque as a cross product, it is a vector, but normally we'll just be thinking about either clockwise or counterclockwise torque. So normally we won't have to worry about the direction of torque in simpler problems like this. So yeah, torque is the equivalent of angular force. I think we motivated that with energy. But now we had force equals ma, right? So now we should be able to define some equivalent for angular motion. Well, we have our angular force, which is torque, and we have our angular acceleration alpha. No, we're just missing what is our mass. Well, it turns out we can't just use mass here. We have to use something known as the moment of inertia. And I will talk about that next. So say we have a particle moving in a circle as usual, and we're applying a force. Okay, just one particle here. And we apply a force. And by Newton's second law, okay, our acceleration is force over mass. Okay, that's very cool. But what about our angular acceleration? And what about our torque? So the torque is F times R, and the angular acceleration is, well, we know that R alpha equals A, so the angular acceleration is A over R. So now what do we get? We'll get that our torque, which is F over M, our torque, which is F times R, is equal to F ma times R, and this will be equal to m r squared times alpha. So now it is in the form that we wanted, which is torque equals some inertial property times alpha. And so this is our moment of inertia here, mr squared. So for a rigid body that's a collection of different masses, instead we'll have the sum of these. And oh, something important to point out is that these are all of the rotational quantities are relative to a certain axis. So let's say we're like spinning around this axis. Well, this will be our R. Let's say we have a triangle of points. How about that? And these are just point masses connected by massless rods. So our total moment of inertia is m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Or if those are our three masses, these are our three radii, and this is our axis. Well, actually, this can change. Like, if our axis becomes here, now we're rotating around that axis, well, all of our radii will increase. So it's always important to pay attention to what axis of rotation you're talking about when you're doing these problems. And there is also the continuous case of our equation, which is that I is the integral of r squared dm. So if we have something like a disk, we can just, and it's rotating around its center, we can just split it into tiny pieces. And for each piece, that's a small mass dm, we just multiply by its r squared. And then take the integral, which is basically summing up everything, And that's how we find the moment of inertia. So let's do some examples. I'll give you a few minutes to think about these. And as always, if you have any questions, you can ask me or send me your answers in the chat. All right, so let's first talk about part A, and hopefully that will give you some idea to as to how to do this. So we have a uniform rod here. It has mass M and length L. Okay, and then we have an axis through its center. So if I draw this in 3D, kind of, this will be the axis and it's rotating around there. Okay. So what is its moment of inertia? Well, it's a continuous rod. We have to use our formula of I equals the integral r squared dm. All right. So what is a small mass element here? Well, if we think about a rod and we chop it up into tiny pieces, and each piece has length dr. Well, what is the mass of each piece? Well, it will just be m times dr over L. All right. And so if we plug this in, what we should get is I equals integral r squared times m times dr over L. And notice that r here, well, it goes from negative r over 2, L over 2, to plus positive L over 2. So those are our limits of integration. So let's do this integral. Negative L over 2 to L over 2, r squared m over L dr. And this will be m over L times 1/3 r cubed from negative L over 2 to L over 2. And if you plug in the limits, you should get that this is equal to 1/12 m L squared. All right. Now, hopefully that gave you some idea of how to do these, how to calculate these moment of inertias for such objects. And so I'll give you a few more minutes to try parts B and C. All right. So let's talk about parts B and C now. Um, so part B is asking us to calculate the moment of inertia. This is also a uniform rod, but it's around an axis through one end. So as I said earlier, which axis it's around changes the moment of inertia. So before we had something like this, now we have something like this. All right, but the equation is basically the same. We just have to change our limits of integration. So before it was negative L over 2 to L over 2. Now it's from 0 to L. So we can use the same formula for it's M over L, 1/3 R cubed from 0 to L. And this is just 1/3 ML squared. All right, part C is a bit trickier because we have a disk. Now a disk is 2 dimensions instead of our 1-dimensional rod. So how would we approach this problem? So we have to split this up into many different masses. And then for each one of these, calculate dm times r squared. So let's first split it up into, how will I do this? Let's split it up into dx's and dy's. Like this is, we're going to integrate in Cartesian coordinates for now, just as an example. Normally, if you know polar coordinates, you can probably see that it's going to be easier in polar coordinates. But just to illustrate, since probably also some of you don't know polar coordinates very well. So we can have a mass at position x comma y, and it's basically a square with length dx and height dy. So what's its mass? Well, that's easy. Since it's a uniform disk, its mass is just m times the area that the square has, dx dy, over the total area of the circle, which is pi r squared. So this is our dm. Okay. Pi, let's use capital R because I use lowercase r for the position or radius coordinate. So now we can try integrating. It will be integrating over our circle. And we have m over pi capital R squared times lowercase r squared dx dy. And in our case, lowercase x or lowercase r squared is just x squared plus y squared. And the reason why this is because, okay, our point here is at x comma y, right? So if you try to find its radius, well, that's just square root x squared plus y squared by Pythagorean theorem. So our r squared is just x squared plus y squared, and then dy dx. And then we can put on limits of integration. So x can go from anywhere from negative r to positive r. And then once you fix x, y will go from root r squared minus x squared to root r squared minus x squared. Oh, that's hard to tell. Okay, I'll rewrite it bigger. R moment of inertia is the integral from negative r to r integral negative root r squared minus x squared root r squared minus x squared m over pi r squared times x squared plus y squared dy dx. All right. And this isn't too hard of an integral, hopefully. I think. Yeah, it looks okay, but it is quite tedious. And by the way, if you do this, you should get an answer of 1/2 mr squared, which is the answer. But there is a faster way, which is using symmetry. So a lot of times in physics, you can use symmetry to make your calculations easier and much quicker and not messy like that. So instead of splitting it up in Cartesian coordinates, what we can do is just split it up into little rings like this. All right. And yes, this is essentially integrating in polar coordinates. So why did we do this? Well, this makes it much easier because in each ring, there's the same radius. So when we consider dm r squared, well, we have the same radius. So we'll just add up all the dm's and then multiply by r squared. So what is the mass of one such ring here? Well, what is its area if it has radius little r and thickness dr? Well, we can think of it kind of like, I guess, a collection of small rectangles. So if we cut it here and unfold it, we'll just get a large rectangle. It has thickness dr and length 2 pi r because that was the original circumference of a ring. So now its area is just 2 pi r dr. So its mass is m times its area over the entire area. And this should simplify to be 2 mr over r squared dr. All right, cool. So now all we have to do is integrate this from 0 to big R. We have 2mr over r squared times r squared dr. And this will be just 1/2 r to the 4th over r squared times m, of course, from 0 to r, which is 1/2 mr squared. So we get the same thing, but it's just much easier this way. All right. Now it is 2:37, which is 7 minutes after 2:30, which is when we were supposed to have our break. But so I'll just give you this big list of stuff. Yeah, we already calculated a few of these. And well, you should know how to calculate all of these, but during the contest, it will be very time consuming to recalculate these every time you need to use them. So I would recommend like knowing some of the, yeah, I would recommend just knowing some of these very common ones so you don't have to recalculate them each time. And with that, I will give you guys a 5-minute break. See you back at 43 after. All right, it's 2:43 now, so let's get started. Um, Now let's talk about two useful theorems because you won't always be given one of these common objects here. So these theorems can help you with that. So the first theorem is the parallel axis theorem. And what the parallel axis theorem is saying is if you have an object, it can be any object. So some weird object like this, and any axis too. Okay, not any axis. The axis has to pass through the object's center of mass. But other than that, any axis through its center of mass. So whatever direction you want. And it's rotating around this axis and it has a moment of inertia I0. If you draw a parallel axis, that's a distance d away, and now all of a sudden it starts rotating around this new axis, the moment of inertia will be I0 plus md squared. M is just the mass of the object. All right, so this theorem's very useful. Okay. And another one, which is slightly less useful, but still kind of useful, is the perpendicular axis theorem. So this is not as applicable to as many objects because this only applies to pancake-like objects. And what it states is that, so we have like a pancake here, and it has to lie in a single plane. So it has to be completely flat. And what it says is that if it rotates around this perpendicular, so I guess in this case, if we define axes, x and y are here and z is here. So say x, y, and z are perpendicular axes, and our pancake lies entirely in the xy plane. What this theorem basically states is that the moment of inertia around the z-axis, which is perpendicular to the pancake, is the sum of the moments of inertia of the x-axis and the y-axis. And the x and y-axis axes actually, they can be any axes as long as they're perpendicular and in the same plane of the object. All right. So let's go on to a quick example of this. Okay, it's been a while. Let's just talk about this. Um, this is actually a relatively simple problem once you see the trick. So what it's asking is we have some disk, an axis. Okay, first of all, it's hard to draw. So we have a disk and it's rotating through an axis around its center. And we just derived a few slides ago that its moment of inertia is 1/2 mr squared. Okay, so now in the case of this, where it's rotating around its diameter, this is very hard to draw, but it will be like spinning like this way. Um, how to draw it? Anyways, it's rotating around this axis now. So what is its moment of inertia now? Well, to do this, we can use the perpendicular axis theorem. So, okay, but this is a bit different because with the perpendicular axis theorem, in its original statement, you know two of these moments of inertias, and you can add them up to get this moment of inertia. But this is actually the same thing. So we know what this is, right? This is 1/2 mr squared. And this disk is actually symmetric. So we know that whatever this Ix will be, Iy will also be the same thing because, well, it's just a circle, right? It doesn't matter because of symmetry. Any axis through its diameter are basically the same things. So the moment of inertia through any axis that passes through a diameter will be the same. Okay, so now we just get that Ix plus Iy is equal to 1/2 mr squared. But since these are equal, we will just get that each one is equal to 1/4 mr squared. All right, and that is our answer. So now we know about moment of inertia. So let's just review a bit. Also, one thing important I forgot to mention in my slides is that, okay, I mentioned this earlier, but it's very important. You have to remember which axis you're rotating around because torque, ooh, that's a big torque. Torque and moment of inertia depend on the axis. So we gotta make sure like torque with respect to this axis, like if we have forces here, then this will be our R. But if it's something like this axis, then okay, this will be our R, and also there's going to be an angle here. So it will be different. But once you calculate torque and I around the same axis, you can use our relation torque equals I alpha. So yeah, this is basically the equivalent of F equals ma for rotation, right? So now we can go on to some rotational dynamics problems. Yeah, okay. Let me draw a diagram so it's a bit easier to see what's going on. All right, where to draw it? Let's try it here. So what we have is, just to clarify, we have a table. Actually, I do have a diagram. So we have a table. Oh, not in the right place. I have a table here, and there's a stick that goes like this. And initially there's a string that's holding it up, but then we cut the string. So now it's going to fall down, right? So the problem's asking for the acceleration and also the normal force from the table here. All right, it's been a while, so let's start talking about this problem. This is quite a tricky problem. Um, so how will we approach this? Okay, if we go back to the diagram I drew earlier, we have the rod that's on the table and it's being held up by a string, but then the moment it's cut, it experiences two forces. First of all, there's the downwards mg, and there's also an upwards normal force from the table. Um, and the tricky part is that this normal force, it's not acting at the center. So it's going to provide some torque, which means that the rod will rotate as it falls, which is kind of intuitive. But let's see if we can quantify this. So let's bring our diagram over. And there are actually two ways to do this. And I did say it depends on your axis, right? All of your quantities for torque and moment of inertia depend on your axis. But actually, they should work no matter which axis you choose, as long as you keep it like consistent, I think. And also, there are some weird conditions like your axis or your reference point. It's either your center of mass or some non-accelerating point, I think. But other than that, just choose an axis that makes the problem the easiest. So in my case, I will actually choose two different axes, both of which are kind of nice to demonstrate two different ways of doing this. First of all, let's look at it from the point of view of the center of mass of the rod. So first of all, we can write F equals ma, right? F equals ma. So the acceleration of the rod, if we have ma, what's the net force? It's just mg minus the normal force. All right. So far, so good. We have one equation, but we have like two unknowns. So we need more equations. And this is where torque equals I alpha comes in. So a torque equals I alpha. First of all, this is a rod, uniform rod around the center. So I is going to be 1/12 ml squared. And what's the torque around the center of mass? Well, the gravity effectively acts at the center of mass in terms of torque. So we don't have to worry about that because R equals 0 for gravity. But we do have to worry about normal force. So the torque from normal force, that's just Fn times the distance, which is L over 2. Oh, that's messy. So Fn times L over 2, that's the torque, and equal to 1/12 ml squared times alpha. All right, that's progress. We have one more equation. The only problem is we have one more unknown. So because alpha is our new unknown here. So how do we find more equations? Well, there's one condition that we haven't used yet, which is it's on the table, right? This is the normal force condition. So this end here, this end can't accelerate into the table. The table will push it back. So now what we would get here is that the acceleration of this point has to be 0 at the moment that we release it. So what's its acceleration? Well, the acceleration will be the acceleration of the center of mass, but also plus our acceleration from the rotation. So the acceleration of that point is ACM, but minus R alpha, right? R alpha is just the acceleration from our rotation. So what we'll get is that 0, A minus, and R here is L over 2. Okay, so finally, we have our third equation, A equals 1/2 L alpha. So we have three equations, three unknowns. We can solve this, right? Ooh. Well, where should we substitute? Let's substitute in this first. So Fn times L over 2 equals 1/12 mL squared alpha. We can divide both sides by L over 2. 1/6 mL alpha. And then this will just be equal to 1/3 m8. All right. Then we can substitute that back into this equation here. MA equals mg minus 1/3 MA. And this will give its acceleration, which should be 3/4 g. And then if we have to find its normal force, we plug this back in. And we'll get 1/4 g. All right, so these are our answers. Mg here, sorry. Oh, sorry, not an mg here. What did I do? Okay, this is acceleration is 3/4 g. Normal forces are 1/4 mg. That should be the answer. Okay, but I said we were going to do a second way, right? We can also approach this problem by looking at it from this point as sort of our reference point. So the advantage of using this point is actually slightly easier because what's going to happen here is that what is the torque from the normal force? Well, there is no torque from the normal force. Its radius is 0. So we don't even have to know what the normal force is yet to do torque equals I alpha. So we will get an F equals ma equation that's the same as before. Ma equals mg minus Fn. But our torque equals I alpha equation will look kind of different. Because first of all, I is 1/3 ml squared now, because we are now a uniform rod around one of its ends, which means this is the moment of inertia. And the torque is just mg times L over 2, because now gravity is just the only force that provides a torque. So now let's write torque equals I alpha, mg L over 2. And we can immediately get that alpha is going to be 3/2 times g over L. Okay, so now what's the acceleration of the center of mass? Well, our acceleration here, that's just our alpha. This is our center of mass is a distance L over 2 from our pivot. So this is 3/2 g over L times L over 2, or 3/4 g. And then from that, we can just plug that back into here to get our normal force mg minus ma, which is 1/4 mg. So we will get the same answers. It's just sort of slightly different equations, but in the end, it'll all work out to be the same. But as you might have seen, one way is slightly easier than the other. So you can, yeah, when you're doing these problems, you can choose your reference point to be wherever you want. So you should choose it wisely to make your work easier. All right, now let's talk a bit about energy and momentum. So we have normal translational energy and translational momentum, but we also have angular rotational energy and rotational or angular momentum. So if we have, let's say we have a mass, it's rotating a distance r away, and so it's going to have some v equals r omega, right? So what's its kinetic energy? 1/2 mv squared. This is 1/2 mr squared omega squared. This is just 1/2 I omega squared. Okay, so what this basically says is when we have an object that's rotating, I don't know, some object, and it's rotating, the kinetic energy associated with that is 1/2 I omega squared. And if it's also moving and rotating, well, we can just add up the 1/2 mv squared, and v is the velocity of the center of mass. We can just add on our rotational kinetic energy, and that will give the total kinetic energy. And what about momentum? So we saw that F in translational motion, we can have P equals mv, right? So the translational analog is angular momentum, L, which is equal to I omega. And oh, can I see slide? If you want me to go back a slide, sure. This is just talking about energy. I will review this. This is actually quite easy to remember because if we think about it, rotation is similar to translation. We just have to replace some variables. So we saw that x becomes theta and v becomes omega and a becomes alpha. And more recently, we defined a torque, which is the equivalent of an angular force. And now we defined a mass that's the equivalent of normal inertial mass. This is moment of inertia. So if we see like equations like F equals ma become torque equals I alpha, or like E equals 1/2 mv squared, this just becomes E equals 1/2 I omega squared. So if you remember like what these things represent, then you can normally easily convert from rotational formulas to, or from translational formulas to rotational formulas. All right. Cool. Let's go on. Yeah, so angular momentum, if we want to define it formally, it is defined as R cross P. So P is our normal momentum. and r is just our distance around some point. And this is also a cross product. So angular momentum is also a vector, but like normally it's either just clockwise or counterclockwise. So just pay attention of this theta here. You might have to multiply by not that theta, but this theta. You might have to multiply by sine theta or something like that. But yeah, angular momentum is the equivalent of normal momentum. So we have momentum is equal to I omega, right? And this is just because if we have, by our definition, L equals RP and P equals MV. So this is RMV, but V is also R omega or MR squared omega. And then, yeah, this is just I omega. And you can do cool things with, it's also, torque is also dl dt. And this is basically the same thing as our force equals dp dt. So this is the Newton's second law for rotation. And just like normal momentum, perhaps the most important thing is that if we have a system of particles and they interact, whatever, normally what happens is that each interaction, well, one particle exerts a force on the other particle, but by Newton's third law, that other particle exerts an equal and opposite reaction force. So if we consider the torques, well, the torques are going to be the same with respect to some reference point because the forces are the same. And also the radii should be like the same. Yeah, so these will end up canceling out and we'll be able to have the equivalent of conservation of momentum for rotational, which is basically just the conservation of angular momentum. So when there are no external torques, angular momentum will be conserved. Yeah, basically what I just said. So yeah, now for the last problem, it is quite a tricky problem, actually. I'll give you a few minutes to think about this one. Oh, wait, yes. This will collide at the end of the stick. I forgot to mention that, but let me draw a diagram again for clarification. So we have a mass m here. Initially, it's traveling at a velocity of v, and it will collide with the end of the stick here and stick to it. And yeah, the stick will move, but it will also rotate. And so we want the velocity of this end right after the collision. All right, it's almost 3:30, so let me start talking about this problem. Um, okay. So let me move my diagram over. Oops. Um, Here. Oop, I kind of gave away some of my work. So how will we approach this problem? The first step is to choose a good reference point. And here I'm just going to choose the center of mass because the center of mass, it's going to rotate around the center of mass after the collision, right? So it's going to be very nice to choose that as our reference point. So first of all, we have right after the collision, what's the center of mass going to be? It's going to be right here. And so let's calculate the moment of inertia first around this new center of mass. So for the stick, we can use the parallel axis theorem and get that I equals 1/12 ml squared plus this distance here is L over 4. So plus 1/16 ml squared. And then we also have to add on another 1/16 ml squared because this mass is also here. It's the distance L over 4 as well. So after we add this all up, we should get 5/24 ml squared. That's our moment of inertia. And okay, we have two equations, I think. First one is conservation of linear momentum. So what that says is that mv, that's our initial momentum, it's going to be 2m times our v final. This is the final velocity of the center of mass, which should move at a constant velocity after the collision. So we'll get that v final is just v over 2. All right. Now we have conservation of angular momentum. So what's its initial angular momentum? Well, to calculate that, we have to use the definition L equals R cross P. So initially, our ball, our mass is the only thing that's moving. So it's the only thing that has momentum. And it has mv of momentum. And remember, our reference point is right here. So this is our R. And so this R cross P is basically just the momentum times the lever arm, or as some people call it. The lever arm is just this distance. That's the kind of the perpendicular distance to the momentum. And this is just L over 4. So our angular momentum is mv L over 4. But this is equal to I omega, and this is after the collision. So after the collision, our omega will be mvl over 4I. And this is equal to, I think it is 6/5 v over L. Okay, so now we're able to solve the problem. The problem was asking for what's the final velocity of the mass. Well, if we look at the stick and mass system, it's going to have a center of mass velocity plus this rotational velocity. Its final velocity, v, will be equal to the center of mass velocity plus r omega. So this is v over 2 plus r is L over 4, and omega is 6/5 v over L. And if you add this all up, you should get 4/5 v, which I believe is the answer. All right, cool. And that is it for my lecture. Thank you for listening. There's some optional homework problems there. You can always find stuff in the book. Other than that, yeah,